All right, good afternoon, everyone. My name is Simon Tao, and I'm a program manager on the Windows AI platform team.
And I'm Clark Rarig, a program manager also on the Windows AI platform team.
So before we get started, Clark and I have a bet going on, and we need your help to settle it.
Yeah, so I have a question. By a show of hands, how many of you have been to 3 or more breakout sessions this week at Build that had AI or ML in the title?
Let's see those hands.
Okay.
All right, Clark, it looks like you have booth cleanup duty after this session.
Bummer.
All right. So we announced the first preview of the Windows AI platform a year ago with Windows 10 version 18.03, and the first public release in version 18.09. The last year has been an exciting and wild ride, with an incredible amount of interest from developers like you. On behalf of the entire team, Clark and I would like to thank those of you who took the early steps to invest and investigate our platform. We hope to keep working with you and learning from you in the future. For those of you who are new, welcome, and thank you for spending your valuable time here with us today. We're going to start this session with a brief recap of why artificial intelligence is important, and then what the Windows AI platform brings to the table to help you solve hard problems. We'll cover some early examples of early adopters who have used the Windows AI platform. And then Clark and I will dive deeper into the 3 main components: Windows ML, DirectML, and the compute driver model. And we'll talk about some of the exciting new features we've been working on based on your feedback. So artificial intelligence, simply put, is the field of making computers think and perform tasks more like human beings. We like to think about the value of AI through the lens of the hard problems that you are trying to solve every day. Many of these problems are relatively easy for a human to solve, but are difficult to program a computer to do. Consider these examples. What if your business needs to figure out whether a customer will renew their subscription or not? What if your application needs to identify certain objects in real time from an image or video feed? What if you need to determine whether parts rolling off of a manufacturing line are defective or not? So these preceding problems all have a few common properties. First, they involve a repeated decision or process which you want to automate and receive consistent results. Second, it is difficult or impossible to explicitly describe the solution or the criteria behind your decision. Third, you do have labeled data, and this is essentially existing examples where you can describe the situation and map it to the correct output. So problems with these characteristics are well suited to being solved by a particular subfield of artificial intelligence called machine learning, or ML. Many of the most exciting and impactful innovations occurring within artificial intelligence today are happening within machine learning. So a typical machine learning workflow breaks down into 2 main phases. The first is called training. And this is where the computer extracts patterns out of your large data sets. Training typically occurs at development time and can either happen on your workstation or perhaps hosted in the cloud. So for example, Microsoft Azure offers several very powerful ML training offerings. And we'll talk more about some of these later in the session. The second phase is called inferencing. This is where the computer uses those extracted patterns to predict the most likely result given a new set of inputs. Inferencing occurs every time a customer calls your intelligent application or service. And this is where we focus. Oh, sorry, I'm going backwards. And this is where we focus. The Windows AI platform is all about being the best way to perform machine learning inferencing on Windows 10. We support running both on your local device and in a virtualized or cloud environment. So as we've worked with developers like you who are solving hard problems, you've given us some consistent and clear feedback about the kinds of things you need in an inferencing platform to be successful. And we've taken this feedback and used them as the principles that guided the design behind the Windows AI platform. First, we offer a combination of practical, practical high productivity APIs and higher power, higher control APIs. On one hand, most of you are probably not full-time data scientists, or you're isolated from your data science team. Your priorities may include ease of development, the ability to incrementally integrate intelligence into an existing code base, or first-class integration with Windows API frameworks. On the other hand, some of you need more power and fine-grained control over your ML execution and are willing to invest in a more advanced API. We provide both API options for you. Second, we give you real-time, blazing fast performance. Imagine you are controlling an autonomous vehicle or drone, or scanning a conveyor belt full of manufactured parts. In these cases, you not only need raw throughput, but you need to minimize latency. And this is the delay between your sensor input and a decision. These are cases where you may not want to take the hit of going over the internet to a cloud-hosted service, and instead you want to perform your ML inferencing on your local device close to the data. And third, we give you the broadest set of hardware that you can target with consistent execution. Anywhere you can run Windows 10, you get access to the Windows AI platform. From embedded and industrial systems like this robot, to familiar PCs and laptops, to HoloLens, to data center class servers. As Windows developers, you probably appreciate the benefits of executing locally on your device. You don't rely on network bandwidth or reliability. You can control and protect your customers' privacy. You also can reduce operational costs because you're not paying for cloud computing resources. But if you want to run in a virtualized or cloud-hosted environment, the Windows AI platform lets you do so with the exact same code base. You can even take full advantage of hardware acceleration when running in a virtualized container environment. And now I'll hand you over to Clark, who will tell you about some early adopters of the Windows AI platform.
Thanks, Simon. So let's talk about a few customers and the way they're using the Windows AI platform to benefit parts of their business. Let's first start with an internal consumer here at Microsoft, with AI-powered ink. Our Intelligent Ink team is continuing to advance intelligent ink using the Windows AI platform, whether it's deploying models locally on the device to do things like handwriting recognition, or, like you see on the screen here, the Microsoft Ink Recognizer service, one of the latest Azure cognitive services which runs on Windows Server in the cloud. They chose the Windows AI platform because it brought them increased engineering efficiency by adopting an in-box API for inferencing and didn't require them to ship their own inference engine with their code. It also accelerated their development cycle by using the same code base to deploy their models locally as they do for their services running in the cloud. These efficiencies can apply to any of you that are trying to run machine learning inferencing on your data, whether that's local on a device or in the cloud on a server. Next, let's talk about Adobe and a new feature they've added to Lightroom called Enhanced Detail. This feature is powered by a trained machine learning model that improves raw image quality through the Windows AI platform. They picked the Windows AI platform because through the power of hardware acceleration, it enabled them to achieve the performance bar they needed in order to ship to their customers. And it provided consistent behavior across various GPU vendors, enabling them to ship to their customers and not have to worry about various hardware configurations. These same benefits can apply to any of you that are deploying your machine learning applications to a wide range of devices with various hardware configurations, because we're consistently working to ensure that you get consistent, and reliable results across the breadth of hardware. And finally, let's talk about Unity, who makes one of the most popular game engines in the world. Unity is using the Windows AI platform to provide ML-powered characters through their Unity ML Agents plugin. This ML Agent plugin makes it easy for developers using Unity to control character behavior with machine learning models instead of using traditional hand animation techniques. They chose the Windows AI platform because it was important for Unity to maintain real-time performance for their customers when running machine learning and rendering workloads together. And the great thing is, this real-time performance scales to any of you that are working on high-performance applications. Now, I want to take a small pause and show you one of the cutest ML agents in action. So this is Puppo. Puppo's movements are entirely controlled by a machine learning model. Each limb is controlled by physics. There is no hand animation involved. Puppo learned on its own to move, walk, and run. And here, we see Puppo chasing after the tasty bones on the robot. So, I hope we can all agree that Puppo is pretty cute, right? But through the power of the Windows AI platform, I can make this demo even cuter with 50 Puppos. So the really awesome thing here is each Puppo you see on the screen is independently powered by its own machine learning model. Each is reacting in real time to its surrounding, whether that's cutting across the grass to try to get to the bones faster or bumping into other Puppos. And all these reactions are working in unison with the graphics rendering work that's producing these cute Puppos on the screen. Now, I'll pass it back over to Simon to talk a bit more about the Windows AI platform technology stack.
Thanks, Clark. So, of course, the secret to our technology stack is that we're actually powered by puppies all the way down. But in all seriousness, the Windows AI platform is a tightly integrated stack of technologies built into Windows 10. Each layer has a specific purpose, and together they give you the combined promise of practicality, blazing fast performance, and hardware reach. Windows ML sits at the top of the stack. This is our API for easily integrating intelligence into your applications. Below that is DirectML, which provides highly optimized hardware acceleration for machine learning workloads. And at the foundation is our compute driver model. This is the common abstraction layer across many different hardware types and vendors. And now back to Clark to cover the top layer, Windows ML.
Thanks, Simon. So, what is Windows ML? Windows ML is an inference engine that we built in to Windows 10, meaning you don't have to worry about deploying a machine learning framework or engine with your app. All you need to do is provide a trained machine learning model, and WinML will provide the best inferencing experience across the breadth of Windows devices. Windows ML also supports ONNX, a standard file format for machine learning models. WinML uses ONNX as our model currency because of its broad support across the ML framework ecosystem, and we've encapsulated the work of the ONNX runtime team. We'll talk a bit more about getting your machine learning model into ONNX in a little bit. With Windows ML, we also designed it with you in mind, the Windows developer, by providing seamless and native integrations with OS components like our media and camera stacks. Plus, WinML is accessible across .NET, UWP, and Win32 applications. Plus, we built a hardware, abstraction, and acceleration layer to make it super easy for you to target the CPU or GPU at runtime, depending on your machine learning workload. And finally, we wanted to make sure we maintained an easy and simple to use API calling pattern. And in fact, I'm going to kick it back over to Simon for a second to walk through our C# object detection sample to see that simple calling pattern in action.
Great, thanks, Clark. So this is the UWP version of our object detection, WinML object detection sample. In this sample, you pass the application an image. Since we love cute animals on this team, we're going to use this photo of a tabby cat. The application then uses its pre-trained ML model to perform object classification. And this is to tell us what kind of object it detects in the image. The model we're using in this case is called SqueezeNet. And this is a common, it's a popular and simple object classifier. So let's dive into some code. The Windows machine learning API model consists of 3 simple steps: load, bind, and evaluate. So I've started the app, and we've hit our first breakpoint, which is load. And this is simply bringing your pre-trained model, in this case SqueezeNet, from disk into memory and into this learning model object. We continue, and we get to bind. This is wiring up your input, the cat image, to the ML model. And there are a couple of API objects to call out here. First, video frame is the Windows camera platform's abstraction to represent an image. Image feature value and learning model binding perform any automatic conversions which are needed to optimally wire up the input. Third, we have evaluate. This is the core inferencing operation. Evaluation may take a long time, a long-running operation, so this method is awaitable to ensure your application remains responsive. And of course, you're going to need to interpret the results that the model returns to you. SqueezeNet, in this case, provides a list of the most probable matches of objects that it detected. And what our sample does is it simply takes the top 3 matches and returns those to the user. So when we let the sample run, at the bottom we have the image of the tabby cat, and we can see that indeed SqueezeNet has correctly identified it as a tabby cat. So in summary, Windows ML provides an easy-to-use calling pattern and great integration with other first-party Windows APIs. This sample and many others are available on the Windows ML samples repo, which is on GitHub. And now back to you, Clark.
Thanks, Simon. So let's talk a little bit more about getting an ONNX model. As I mentioned, ONNX is a standard model format, and there are many ways to get a trained ONNX model. I'm going to touch on 3 offerings that you can use today to get a model for use with Windows ML. The first is Azure Machine Learning Service, which provides an end-to-end solution for preparing your business's data and training your own custom machine learning model. All you need to do is specify you want to save the model into the ONNX format at the end of training. Another option is using Azure Custom Vision to create your own image classification models. It's as simple as uploading your own labeled images, retraining the model with that data, and exporting to ONNX. And finally, if you're using a training framework like TensorFlow, Keras, or any of the other frameworks you see on the screen that doesn't directly produce an ONNX model, WinML Tools makes it easy to convert your trained model to the ONNX format for use with Windows ML. In addition to the Windows ML Tools converter, we have a set of tools that makes it easy to work and integrate your machine learning model into your app and start using Windows ML. The first is WinML Runner. It's a standalone command line tool making it easy to test loading, binding, and evaluating your model without having to write any code. This is great when you're iterating on a trained model or testing out various hardware configurations. When you're ready to bring your trained model into your app, the WinML code generator Visual Studio extension will help you get started by generating wrapper classes to help you load, bind, and evaluate the model in your UWP app. And finally, we have WinML Dashboard, which is a GUI-based tool that'll help you visualize and edit your trained models. Plus, it has WinML tools and WinML Runner built in, giving you the ability to visualize, edit, and run your trained machine learning models all in one app. All of these tools are designed to make it easy for you to get started with your own machine learning models and utilize Windows ML for inferencing. However, we've heard feedback from many of you that you're also interested in having pre-built functionality backed by machine learning models that's easy to integrate into your apps. And that's why I'm excited to introduce Windows Vision Skills. These are pre-built functionality for tackling common computer vision tasks and will help your app get up and running to harness the full power of Windows ML. Let's talk a little bit more about the vision skills that are available for download and use today. The first is object detection. In a given image, it'll help you identify the box occupied by an object and its classification. Also available is skeletal detector. By providing an image, it will return the location of points of interest on a human body, like the nose or elbow. And finally, we're providing sentiment analyzer, which results in the highest probability emotion, like happy or sad, for a given image. Each of these skills can be downloaded as a NuGet package and easily integrated into your app to get you started using machine learning. Plus, more vision skills are coming soon, so be on the lookout on the Windows Vision Skills samples repo. So far, we've touched on the various paths to get started with Windows ML. And not only are we focused on making it easier to get started, but we're continually improving the platform to make sure your apps using ML inferencing continue to see improved performance. Without having to change any code without you having to change any code, we've added optimizations, graph fusions, and additional tuning across both our CPU and GPU paths to help you get the best performance out of any hardware configuration your app targets. All these performance gains are amplified through the great co-engineering work done between our team and various hardware vendors. Based on our own internal tracking, we've seen impressive throughput improvements from our initial preview in Windows 10 version 1803 to our current release, version 1903. Looking under the cover a bit, these performance gains on the GPU path are leveraging the power of a layer that we call DirectML. So, what exactly is DirectML? As I mentioned, DirectML is what's been powering Windows ML's GPU acceleration since its initial release. And this hardware acceleration layer is built as a part of DirectX and fully leveraging 2 decades of experience our team has getting the most out of hardware. And building on DirectX is what's enabled that broad hardware support available to Windows ML. And finally, we built DirectML with real-time performance in mind by having native and seamless integrations with D3, D12, and taking advantage of hardware and architecture-specific optimizations when possible. As we talk to you and other customers about the DirectML layer and how it powers Windows ML, we heard your feedback. You wanted access to the goodness that comes with using DirectML. And that's why I'm also excited to announce that based on this feedback, in Windows 10 version 1903, you'll have access to DirectML as its own API, making it the newest API in the DirectX family. And the super great thing is customers are already using it. You guys remember Puppo up at the start of the deck? Puppo is running on top of Unity's Inference engine, which is harnessing the hardware acceleration power of DirectML. This is just one example of a high-performance application tapping into DirectML. So, you might be asking yourself, when should I use DirectML? For most scenarios, we think Windows ML will be a great fit for your app's needs. But there are some cases where you should consider using DirectML. DirectML is great if you're wanting access to an operator-level API instead of the Windows ML model-centric API. Plus, with DirectML, the set of operators supported aligns with the ONNX 1.3 standard and will continue to evolve with the standard and your needs. Additionally, DirectML is great if you're looking for more control and flexibility. We give you the ability to schedule your own operator calls together as you see fit and manage the lifetime of all resources and memory allocations. DirectML is also great at enabling the interleaving of ML workloads with existing D3, D12 rendering workloads in high-performance applications. And finally, if you're working on a graphics or inference engine, then DirectML can help provide hardware-accelerated inferencing to you and your customers. Now, I'll pass it back over to Simon to talk about the lowest layer of the Windows AI platform, the compute driver model.
Thanks, Clark. So the compute driver model sits between the rest of the Windows AI stack and the underlying hardware accelerators. And it defines how those two components communicate with one another. If we do our job right, you will never need to directly interact with the driver model, since you will be using higher-level APIs, such as DirectML and Windows ML. But this layer provides a few critical benefits to your applications. First, the hardware abstraction layer is what enables Windows AI to run on the enormous diversity of hardware that we've talked about earlier. Whatever the type of hardware accelerator, whatever vendor or architecture, and whatever device generation your workload is running on, we give you the confidence that your models and workloads will return consistent and conformant results every single time. Second, our driver model enables core OS services. This includes multitasking support, power and memory management, and process isolation. Now, these are things that have been solved on the CPU for many decades. But on GPUs, for example, they really didn't exist in a generalized manner until we introduced the first version of the Windows Display Driver Model, or WDDM, about 15 years ago. More recently, we've been working on robust virtualization support. And now, with Windows Server 2019 and Windows 10 version 1809, you can run Docker container workloads and seamlessly share access to the GPU with your host and other guests. And of course, our driver model relies on hardware vendors to write Windows drivers for their devices. As Clark noted, we have over 2 decades of experience co-engineering with partners such as AMD, Intel, NVIDIA, Qualcomm, and others. It's only because of these long-lasting partnerships that we can achieve things such as those impressive throughput gains you saw with Windows ML earlier in this session. Now Clark is going to show you just how easy it is with the Windows AI platform to migrate your machine learning workloads between the diversity of our supported hardware. Over to you, Clark.
Thanks, Simon. So here we have a console version of the object detection sample Simon was showing earlier. I want to draw your attention to this line of code, where we're selecting the learning model device kind. This is the one line of code you need to change to target different accelerators on a system. As you can see, right now, we're targeting the CPU. But let's say I wanted to target the default GPU on a system. It's as simple as switching the learning model device kind to DirectX. It's because of our hardware abstraction layer that it really is that simple. Now, I've taken this sample and changed this one line of code to be able to target the 4 different accelerators that we have here on the system. So earlier I pulled up Task Manager, and we can see that we have a CPU here. We have an integrated GPU. We have a discrete GPU. And we have an AI accelerator. And Simon will talk a little bit more about AI accelerators after this demo. So, as I mentioned, I compiled 4 different versions of this demo that you can see here to run continuously against the 4 accelerators. So I'm going to go ahead and launch these. And as they're starting up, let me go ahead and move back over to Task Manager here. And now you can see that each of the accelerators in the system is starting to run and process their respective machine learning workloads. See it on the CPU, the GPUs, and the AI accelerator. Now, I'm going to take this one step further and take that same discrete GPU sample and show off the power of GPU virtualization by running it inside of a container. So I have a pre-built image here that I'm going to launch and run, and it's going to take that same discrete GPU sample and be able to access the host system's discrete GPU in the same way as the physical OS. And so, as you can see over here in Task Manager again, the discrete GPU is starting to run that machine learning workload that's inside the container. So, ultimately, what we're hoping that you take away from this brief demo is that it's really that easy by just changing that one line of code to be able to target the right accelerator for your machine learning workloads when you deploy with the Windows AI platform. Now, I'm going to pass it back over to Simon to talk a little bit more about those AI accelerators.
Great, thank you, Clark. So we're seeing an exciting wave of innovation from the hardware ecosystem, as many companies are starting to produce specialized processors to accelerate AI and data parallel workloads. In much the same way that GPUs help to make graphically rich user experiences ubiquitous, we think that this new wave of hardware will help to accelerate, no pun intended, AI adoption in the computing landscape. We are taking our heritage of our expertise and technology running on the GPU and extending that to this new class of data parallel processors. And because our driver model provides a robust hardware extraction, if you are using a higher level of the stack, such as DirectML or Windows ML, you will automatically get access to these new devices alongside existing CPUs and GPUs, with the same guarantees of consistent execution. The first AI-focused accelerator that the Windows AI platform will support is the Intel Movidius Myriad-X Vision Processing Unit. As you probably guessed, the AI accelerator demo that Clark just gave was running on a Myriad-X VPU on this PC right here, with a pre-release build of the Windows AI platform and a pre-release Intel driver. The Myriad-X VPU is all about power-efficient ML inferencing and is optimized for two kinds of scenarios. The first is offload. In personal computers, your CPU and GPU will often be busy with computationally intensive tasks, and a VPU can increase the availability of ML execution resources. The second is background processing. These are long-running tasks, for example, wake on voice or anomaly detection in a video feed, where you want to minimize power consumption over time. Our engineering teams have been hard at work over the last year to light up the Myriad-X VPU on Windows. For those of you who want to try VPU support yourself, we're excited to announce that the first developer preview will come in the next couple of months. And you can find out more at Computex, which is at the end of May. All right, so let's wrap up. We've shown you how the Windows AI platform is the best way to perform ML inferencing on Windows 10. Our stack consists of Windows ML, DirectML, and the compute driver model. And together, they give you practical and powerful inferencing API options, real-time hardware accelerated performance, and broad hardware compatibility with consistent execution.
And although we are near the end of build, we wanted to include a handful of references to other breakout sessions that have happened over the past couple of days that cover some of the topics we mentioned in greater detail. And also, if you haven't already, stop by the Windows AI platform booth after the session. I'm going to be cleaning up, and we're right underneath the AI sign in the hub. Plus, Simon and I will hang out after the session if you guys have additional questions. And finally, here are the links to our documentation, samples, and tools to help you get started with the Windows AI platform and your application. Also, as you're working with the platform, don't hesitate to reach out to askwindowsml@microsoft.com for any questions or feedback. Thank you so much for joining us today to hear and learn more about the Windows AI platform. And on behalf of the whole team, we look forward to seeing you use the platform to build great AI solutions. Thank you, guys.
If people want to come up to the microphone. Oh.
Yeah. Okay. So the models that you build with the .NET ML, it creates a zip file. I'm not sure if it's an ONNX model or not, but then, it runs. But it doesn't use your APIs. It uses its own API. So I was just wondering, is it different? Is it the same?
Yes. So ML.NET you can use to basically do training and inferencing.
Right.
And so
I'm talking about the inferencing part.
Yeah. And so with ML.NET, you can produce ONNX models depending on the path that you take. And so those ONNX models you can either deploy with ML.NET depending on the scenarios that you're deploying to, but you can also use those same ONNX models and deploy them with Windows ML and get the benefits of the hardware abstraction and acceleration there.
So by default, those zip files are not ONNX models, right? My understanding.
I am not confident in exactly what the default is, but I know that you can export from ML.NET to ONNX. Thank you.
All right, if there are no further questions, I think we can adjourn then. Thank you very much, everyone. Enjoy the rest of Build.
Yeah, have fun.